Hi there, I'm Thomas from IndustrySim. In this video, I will discuss on how a skilled engineer would operate the electric grid in the Vellamo Cliff scenario. So, let's look into things from the viewpoint of an engineer, and we need to start by switching on the engineering mode in our brains. The player's achievement is calculated from the economic performance. That is, the bottom line of the operations. So, let's take a look on how to reach a high bottom line during our work shift as the grid operator. Let's have a closer look at the setup of the Vellamo Cliff energy infrastructure. Please see the Vellamo Cliff screen view at the left and the corresponding flow scheme on the right. We can see all the production utilities in the scheme as well as the consumers. The IoT control server is what makes this electric grid smart. Let's have a closer look at each production utility, and let's also elaborate the properties of the consumers of electricity. By the way, the Vellamo Cliff is a good case where artificial intelligence in combination with IoT shows to be very useful. Please note that there could also be many more feasible ways to store electric energy than a pumped storage. Also observe that if there is an imbalance between production and consumption, then the price will drop, which is very bad for the operations. It is not said what specific type of power unit the thermal plant is. It could, for example, be a gas turbine or a diesel engine. The most important property of the thermal plant is that it supports a fast ramp-up of power so that it can work as a control power unit. The other thing that should be pointed out is that the power level of the thermal plant can't go lower than half megawatt. Please bear in mind that the operational costs of the thermal plant are high due to expensive fuel. There is a high investment cost for the wind park, but the operational costs are low. The production of electricity is consequently dependent on how the winds blow. It should be stressed that the wind turbines cuts off the production at very low and at very high wind speeds. The operator needs to use all the wind power available as efficiently as possible to pay off the high capital costs. If there is more production than consumption, then the surplus needs to be stored, either as pumping it up to the lake or as heat in the water tank in the houses. It is paramount to follow the weather forecasts very closely to be able to constantly update the daily operational plan. The hydroelectric turbine is the energy producing part of the pumped storage system. It should be noticed that the power output from the hydroelectric turbine is controlled by the flow gate, which works as a valve, meaning 100% open gives maximum water flow and power output. Please note that the flow gate could also be less opened than 100%, leading to a lower water flow and power output. All the water flowing through the hydroelectric turbine must first be pumped from the river up to the lake. Please test how fast the lake will drain when keeping the flow gate open. Please have a look on how the efficiency on the pumped storage should impact the operational strategy. The pump is equipped with a variable frequency drive, which allows the change of the power of the pump. This gives the operator a better opportunity to optimize the grid, since the power used by the pump can easier be matched to the surplus of electricity in the grid. Please note that there is a big head in the conduit, meaning the pump needs a lot of power before it is able to lift water up to the lake. Try out how the variable frequency drive works by making a change and look at the impact of the new settings in the graphs. The IoT control server is a central computer on which the grid optimizer program is running. This is a very good and helping tool for the grid operator. The three settings works as follows. The optimizer sends to the IoT device of each house a set of commands. These commands are dependent on the settings made by the operator. If the optimizer is not enabled, then no commands will be sent to the houses, which is not in favor of the optimal grid operation. There are three values which the operator can change. Please see menu in the southeast corner of this slide. The water tank temperature set point for the houses can be adjusted between 65 degrees Celsius, 149 Fahrenheit, and 75 degrees Celsius, 168 Fahrenheit. The optimizer sorts the houses in order based on the measured water tank temperature and put the values into a vector V, in which the first element is the house with the lowest water tank temperature and the last with the highest temperature. When the set point is 65C, 149F, then the houses in the first half of the vector V will receive a switch heating on command, and consequently the rest of the houses in vector V will receive a switch heating off command. When the set point is 75C, 167F, then all the houses in vector V will receive a heating on command. The number of houses receiving a heating on command will be interpolated linearly for set points between the min and max set point value of the tank temperature. The heating power in the houses can be adjusted between 7 and 9 kilowatts. Please note that the internal heating control system in each house can override the commands from the optimizer. The internal heating control system will always switch off the heating when the water tank temperature reaches the set point. The optimizer sends out commands to all houses in a certain interval named heating duration. This interval can't be too short, since that would occupy too many system resources. It shouldn't be too long either, since then the algorithm would lose its edge. The optimal heating duration lies in the range of 30 seconds to a few minutes. Please make a flow scheme for yourself and ponder what would be the best optimization strategy in this case. Once we get the artificial intelligence shell up and running, then a totally new window of opportunity will open to make the optimization smart. So please stay tuned, and meanwhile remember to read the written guide about Vellamo Cliff. The current measurement values, etc., of the houses can be viewed in the Construction tab. Use the lens to zoom in the house of interest and click on it to view the data. The houses are all electric heated and do have a sophisticated heating control system, taking care of many tasks in the house. The water temperature going to the radiators is following the ambient temperature. Please see the heating system setup and the radiator water temperature versus the ambient temperature at the left. The heating control system is also an IoT device. I would like to encourage you to read the instruction guides for playing Vellamo Cliff thoroughly. If you don't have them, please drop me a line and I'll send you links for downloading the PDF files. I really like to hear some feedback from you. So please drop me a line at thomas.rosin@industrisim.com. Hope to hear from you soon. Thank you for your attention and bye-bye.